Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome to lecture 4, Organic Chemistry 2. We are still on chapter 1, Conjugated by Systems and Pericyclic Reactions. In the previous lecture, we covered the molecular orbital description of cycloaddition reactions. Today, we will talk about the electrocyclic reactions. Electrocyclic reaction is defined as the formation of a single bond between the terminal atoms of a linear conjugated system of pi electrons and the reverse. So we have here conjugated pi system, double, single, double, single, double, and we in the terminal, okay, in the term we are forming a new sigma bond. Okay, so we take one double bond from the triene, and the product will be cyclic and diene. The other way around, we can have the ring opening like cyclobutene. This single bond will open, and one extra double bond will be formed. So we started with cyclobutene and end up with buta-1,3-diene. All right. Stereochemistry and orbital symmetry. Electrocyclic reactions are completely stereospecific. You start with one geometrical isomer and you get one product. Okay? If you use the other isomer, you end up with another product, not the same. So, if we start with 2E, 4Z, 6E octa, 2,4,6 triene, heat this molecule, you end up with cis 5,6 dimethyl cyclohexa 1,3-diene. Not the trans, no way. Okay? If you start with 3R, 4S, 3,4 dimethyl cyclobut 1-ene, which is cis, the two methyl are on the same side, okay, you end up with 2Z 4E. You end up with trans cis, trans and cis. You will not end up with trans-trans. Okay, just only one isomer. Stereospecific reaction. If you start with the trans, or 2E, 4E, if you heat it up, you get the trans product. If you shine it with UV light, you get the cis product. Well, is there any explanation for this behavior? To understand these results, we must focus on the HOMO of the acyclic conjugated polyene. That is either reactant or product. All we have to concentrate on is the HOMO of the acyclic conjugated polyene. We examine the p orbital on the terminal carbons of the HOMO and determine whether like faces of the orbital are on the same side or on opposite side of the molecule. Here the red faces are on the same side. Here the red faces are on opposite sides. We call this on the same side and we call this on opposite side. An electrocyclic reaction occurs only when like faces of orbitals can overlap to form a bond. Such reaction is symmetry allowed. An electrocyclic reaction cannot occur between orbitals of opposite phase. Such the reaction is called symmetry forbidden. To form a bond, the p orbitals of the terminal carbons must rotate so that like faces can interact to form a new sigma bond. Two modes of rotation are possible. When like faces of the p orbitals are on the same side, here is red, on the same side with red here, okay? For these two blue to get together head to head, okay, we must rotate this p orbital clockwise, okay, so the blue will move up, and here again we have to move this p orbital counterclockwise for these two blue to meet each other and form sigma bond. We call this disrotatory. One will move clockwise, the other will be counterclockwise in the opposite direction. We call this disrotatory. Now, if we have these two terminal b orbital, the faces are on different sides, okay? To have the blue one, this blue face, matching each other head to head, we have to move here clockwise, we have to move this one clockwise, so they will meet together and form a sigma bond, and we call this fashion counter-rotatory fashion. Okay, so when like faces of p orbitals are on opposite sides of the molecule, the two orbitals must rotate in the same direction, both clockwise or both counterclockwise. Rotation in the same direction is said to be conrotatory. Now, let's examine the thermal electrocyclic reactions. We consider the HOMO of the ground state electronic configuration. Rotation occurs in this rotatory or conrotatory fashion so that like faces of the p orbitals of the terminal carbon of this molecular orbital combine. The number of the double bond in the conjugated polyene determine whether rotation conrotatory or disrotatory. The number of the double bond will indicate what are the shape of the terminal p orbital. Okay? So if we have here the diene, which means that you have an even number 2 pi bond, even number. Remember that the psi 2 is a HOMO, right? And the terminal will be an opposite direction. These two faces, these two carbons are the terminal, and these two faces, red and red, are in opposite direction. Okay, that's in thermal. Okay. In photochemical reaction, we take one of these, we move it to psi 3, and psi 3 will be a new HOMO. A new HOMO in photochemical reaction. In this case, these two faces are on the same direction. Okay? Right. Now examine the case when we have triene 3 pi bond. The psi 3 under thermal condition will be the HOMO, and the terminal will be on the same side. Terminals will be on the same side. Under photochemical, when we take one of these electrons, move it to psi4, and psi4 will be a new HOMO. Now the terminal b orbital, the faces will be on different direction, up and here is down. Okay? You have to remember that the system with even number of electrons, the HOMO will be on different direction. The same faces, okay, of the terminal b orbital in bi system with odd number will be on the same direction. Two examples illustrate different outcomes. Thermal electrocyclic ring closure of 2E, 4Z, 6E, octa 246 triene, this molecule, when we have here methyl group, double bond, single bond, that's E, and then here we have double bond, single bond, double bond, okay, that is Z, and then we have another double bond, CH3 in here, and this group that is E, so E, Z, E. This compound contains 3 bi bond, odd number, so the terminal carbon like faces will be on the same side. Accordingly, to match the like faces together to form a sigma bond, we have to have this rotatory, so in different direction. This one will be clockwise to get the blue in here, and then to get the blue in this side we have to go counterclockwise, so they are matching and making a sigma bond. When we move this orbital this way, the CH3 will be down, and to move this face, this b orbital this way, the CH3 will be down, and the product will be cis as the only product. Thermal electrocyclic reaction occur in a disrotatory fashion for the conjugated polyene with odd number of bi bonds. Now, in contrast, thermal electrocyclic ring 2E, 4E, 24 hexadiene forms a cyclobutene with trans methyl group. Why? Because we have here terminal b orbital and 2 bi bond, it's even, so the like faces will be in different directions. So to match them, to let them match to form sigma bond, one will be, see here, clockwise, and this one also will be clockwise, so the blue shapes will be together to form sigma bond, and we call this conrotatory fashion. If we move this b orbital this way, it will take the CH3 with it, and CH3 will be down, and this CH3 is moving this way, it will be up, and we end up with trans 3,4-dimethyl cyclobutadiene. Thermal electrocyclic reaction occurs conrotatory fashion for the conjugated polyene with even number of pi bond. Since electrocyclic reactions are reversible, so if we have here this one double bond in cyclic form, it will be diene in the open form. Accordingly, since it is coming from the diene, where the HOMO will be, these two faces, like faces, will be a different orientation, then we have to open this conrotatory. So this will be conrotatory counterclockwise, and this will be counterclockwise to get the p orbital again, the like faces at different direction. If you have CH3 down, CH3 up, which means trans, then when you open this, you will end up with 2E, 4E. Trans or E, and again this with that in E. But if you have it cis to start with, and you have to go conrotatory to get these faces at different directions, then you will have the CH3 going up this way, and this CH3 going down, so it will be this way, so it will be Z in this one and E in that one, 2E 4Z hexa 2,4 diene. Draw the product of each thermal electrocyclic ring closure, compound A and compound B. To solve this problem, we have to start first count the number of pi bond in the conjugated polyene to determine the mode of ring closure. If the number of conjugated pi bond odd, then the ring closure will go disrotatory. If the conjugated pi bond even, then the ring closure will go conrotatory. In this case, a triene pi bond, 3 pi bond, that's disrotatory. This will go this way and this will go this way. Here, 2 double bond, so it's even conrotatory this way and that way. Okay, to really see it much more clear, we use the frontier molecular orbital. In case of the triene, we will have the terminal b orbital, the faces are in the same direction. So to get these blue together, we have to go disrotatory, this clockwise, and this is counterclockwise to match here and form a bond. Accordingly, when this goes this way, CH3 will go down, and when this goes counterclockwise, the CH3 here goes up, so we will have the trans product. In case of the diene, the terminal orbital, b orbit, will be the like faces in different directions, and we have to go conrotatory. This one will go this way, so the blue will go up, and the CO2, the ester functionality here, will go down. For the ester group, this again will go clockwise since we are doing counter-rotatory. So the blue will go down, this will go up, match and form a bond, sigma bond. The ester will go up, and that will lead to trans product, down and up. Photochemical electrocyclic reaction. A photochemical electrocyclic reaction follows similar principle as those detailed in thermal reactions. However, in الهومو اللي هي excited state في الفوتو has an opposite orientation of the outermost p orbitals compared to the HOMO of the ground state. As a result, the method of re-enclosure of the photochemical electrocyclic reaction will be the opposite to that of the thermal electrocyclic reaction, with the same number of pi bonds. Remember that we have here phi 2, psi 2 is HOMO in the thermal reaction, where the two faces, like faces, are in different directions. In the photochemical reaction, however, the like faces will be on the same direction, since the psi 3 will be the new HOMO. This is in the 2-pi system. In the even number, in the odd number system, psi 4 will be the HOMO, the new HOMO, and we will find that like faces are now in the opposite direction. Before, in the thermal, they were in the same direction. So in photochemical reaction, the triene will have the like faces on different directions, so we'll have counter-rotatory fashion to combine the two blue ones. One will be clockwise, the other must be clockwise. Okay, so these two faces, the blue one will catch each other and form sigma bond. So methyl group will go down, and this methyl group will go up, and the product will be only the trans isomer product, only trans isomer product. In the even number of pi bonds, here like faces are on the same directions, so to match or to catch these two like faces together to form sigma bond, we have to do the reaction disrotatory. This will go clockwise, anti-clockwise, and this one will be clockwise. So the blue will match. Going this way, CH3 will be up. Okay, it's up. And going this way, CH3 here will go up. Yeah, it's up. And we will get up with only cis product. Only cis product. Woodward-Hoffman rules for electrocyclic reactions. If the number of the conjugated pi system even, we take the thermal reaction counter-rotatory fashion. In photochemical reaction, disrotatory fashion. The system with odd number of pi bonds, thermally we will take it disrotatory, and for photochemistry we will take it counter-rotatory fashion. For this brilliant work, Ronald Hoffman co-won the Nobel Prize in Chemistry in 1981 with Foucault. Identify compound A and B in the following reaction sequence. Label each process as conrotatory or disrotatory. This compound is cyclic compound. Thermally it will open. A system will be losing one sigma bond and add to it one pi bond with slight ring closure again. That's what I'm expecting. Now, if it comes from the triene open structure, then these like faces on the terminal triene will be on the same side, right? To do that, we have to take the sigma bond in this rotatory fashion to open the sigma bond to this new b orbitals, where like faces are on the same side. So this will go counterclockwise, and this one will go clockwise. So the trans methyl groups will open, one on this side cis, or we call Z, and the other one here trans or E. So that's a compound A. Now when we shine it with UV light, the HOMO will change. Two like faces are on the same side, switch to different directions. That is the new HOMO. Then we close that system, forming again sigma bond. This should go conrotatory fashion. So if this is counterclockwise and this counterclockwise, okay, so the blue will come this way and the methyl group will go down. Here the blue will go up and the methyl group will go down. So here is down, here is down, down and down, and the product will be cis. So for trans 5,6 dimethyl cyclohexa 1,3-diene, to transform this molecule to cis, first we heat it to open, form compound A, and then we give it light, shine it photochemically, and get the product, the cis isomer. Heating cis 3,4-dimethyl cyclohexene A in the presence of dienophile B gave exclusively diastereomer C. Explain by mechanism. We look for the molecular formula C. We will find that it's C10H12N2. It's exactly as we sum the molecular formula of A and B. So this is cycloaddition reaction. And since we have cyclohexene, most likely it is Diels-Alder product. So what is the starting material of this Diels-Alder product? So retrosynthetically approach this compound with double bond. So this one will be number 1, and this is number 4, and we cut here and we cut here. So here is our diene and here is our dienophile. I put them in this way to follow the rule which we mentioned before. This is outside, that's why it's in the back. This is outside, again in the back. Here is inside, so it's up, and this metal is up, so it is inside. The cyano should be endo, so it's down, so we will do it this way. Already they gave us this molecule, and how we can obtain this one? From the thermal product of the cis dimethyl cyclobutene. He gave us the open structure with 2 bi bond, so this should go conrotatory. Yes, that's right. Conrotatory to open the methyl will be up and the methyl will be inside. We can see that clearly if you use the frontier molecular orbital. Here is closed and they are cis. Should open that the two faces, like faces, will be in opposite direction. So we go counterrotatory, anti-clockwise or counterclockwise. The methyl group will be in here, right? And this methyl group will be in here. Yes, that's right. So we get one Z and one E, double bond, right? That's it. One E and one Z. So now it's very clear that this starting material will ring open first to that one. That diene will react with the dienophile to give the product via this transition state where the cyano endo positions and easy diene combine together. See you in next lecture.